Hello, this is section 4.4. I'm going to do a couple of example problems from this section. One of the things that I want you to be able to do is to determine the equation of a polynomial function based upon certain conditions that we give you. In this first example here, I give you the conditions about zeros and their multiplicity and passing through a point. And I want you to write its equation. And I want you to write its equation in complete factored form. And by and large, that's what I want, is for you to write the equation in complete factored form. So if you take a look at this first example, we've got a fifth degree polynomial. Its first zero is at -2. Well, since it's at a zero at -2, then x plus 2 must be a factor. Multiplicity 2. Since the 0 of -2 has a multiplicity of 2, then this factor of x plus 2 must be squared. The next 0 is at 1. Well, since we have a 0 at 1, then x minus 1 is a factor. And since this 0 is a multiplicity of 1, we're just going to raise this factor to the first power. You don't need to write the first power, but I'm going to write it just to be official. And we've also got a 0 at 4. So since there's a 0 at 4, x minus 4 is a factor. Multiplicity 2 means we're squaring it. And if you add those exponents, 2, 1, and 2, 2, 1, and 2, total of 5, and we're supposed to have a fifth degree polynomial, so we're good. Now, there's an infinite number of fifth degree polynomials that have these conditions. And so one of the things that we're going to need to look at is this value of a, its lead coefficient. And that's where that last part of the problem comes in. I tell you that it's passing through the point 2, 15. So we need to solve for a. And the way we're going to solve for a is we're going to plug in the point 2, 15. When x is 2, y is 15. And then we still have a. We're solving for a. 2 plus 2 is 2 plus 2 is 4. 4 squared is 16. 2 minus 1 is 1. 2 minus 4 is -2. -2 squared is +4. So 16 times 1 times 4 times a is 15. 16 times 1 is 16. 16 times 4 is 64. And so we'll divide both sides by 64. And we get a equals 15 over 64. So our final answer, our polynomial written in complete factored form, that's our value of a, 15/64. X plus 2 squared, x minus 1, and x minus 4 squared. That's your fifth degree polynomial in complete factored form. All right, let's take a look at another example. Here's a graph. Rather ugly looking graph, but it's still a graph. And one of the things we want to do is determine its equation in complete factored form. In the last problem that we just did, I gave you the x-intercepts, those zeros, and their multiplicity. And then from those x-intercepts and their multiplicity, we were able to determine their factors. Here, we're going to do the same thing. We're going to determine the values of those x-intercepts and their multiplicity. If you take a look at this graph, there seems to be an x-intercept here, an x-intercept here, and an x-intercept here. So it looks like we've got an x-intercept at x equals 0, an x-intercept at x equals 2, and an x-intercept at x equals 4. Now we need to determine the multiplicity of each x-intercept. If you take a look at x equals 0, our graph shoots right through the origin. And if you notice, our graph shoots through the origin just like it's a straight line. Well, straight line is multiplicity 1. So x equals 0, that x-intercept at 0 has a multiplicity of 1. I'm just going to write the letters MULT for multiplicity. Take a look at our x-intercept at x equals 2. Notice our graph comes down and does that sideways crossover and then comes down again. When our graph does that sideways crossover and comes down, that's acting like a cubic. And so that at x equals 2, our graph is acting like a cubic function. This has multiplicity 3. At x equals 4, notice our graph looks a whole lot like a downward pointing parabola. Key part is it's acting like a parabola. Notice that it's a pretty sharp parabola. It's not a flattened out parabola. If it was a flattened out parabola, we might think maybe it's got a multiplicity of 4. But this looks like a pretty sharp parabola. So we're going to say that's a multiplicity of 2. So with this information, we can now put together the factors and the exponents on those factors. And I'm going to come down here. Don't forget that lead coefficient of A. Our first x-intercept is at x equals 0, so the factor is just x minus 0, or plain old x. We have an x-intercept at 2, so x minus 2 is a factor. It's got a multiplicity of 3, so we're going to cube it. And then our last x-intercept is at x equals 4, and it's got a multiplicity of 2. So x minus 4 squared. Now we need to determine the value of A. In order to determine the value of A, we need to pick off a point. Find a point that has a nice, neat, whole number x and y coordinates. So I'm going to put on my glasses again and scan through. And I notice right down here, there's a nice point right down there that has nice, neat, clean x and y intercepts. So I'll use that one. Coordinates to that point are 3, negative 3. When x is 3, y is negative 3. So negative 3 equals a times x, which is 3. X minus 2 cubed. And x minus 4 cubed. Or 3 minus 4 squared, I'm sorry. That's a squared. All right, negative 3 equals a times 3. 3 minus 2 is 1. 1 cubed is 1, so 3 times 1. 3 minus 4 is negative 1. Negative 1 squared is 1. So we have negative 3 equals 3a. Divide both sides by 3. And we get a equals negative 1. So we're now ready to type in the final answer for our expression. And I'm going to go to this next screen because I'm out of room. A is negative 1. And we have x times x minus 2 cubed times x minus 4 squared. And that's the equation of the polynomial in that graph. All right, hope these two examples help you in figuring this stuff out. Until next time, take care.